Section 9.2 is about parametric equations. X equals f of t, y equals g of t, no talk of vectors. We did think of those things in terms of points, plotting points in the plane, using parentheses instead of pointy brackets. We thought about particles moving through the plane or through even three-dimensional space. What kinds of problems did you have? Should you be able to, for example, parameterize the ellipses and hyperbolas? Probably keep it to ellipses. Those kinds of equations. This does include circles. It'll be a circle if A and B are the same. H and K are the centers of the circles. If you leave the input for cosine and sine as just a plain old t, it's going to make one revolution around the circle counterclockwise in 2 pi units of time, because those are periodic functions of period 2 pi. If you want to make them go faster around the circle, like twice as fast, replace the t's with 2 t's. 3 times as fast, replace the 3 t's with 3 t's. What if you wanted to go clockwise instead of counterclockwise? Replace the t's with negative t's. That'll do it. Can that be simplified if you do that? Yeah, because cosine of negative t is cosine of t. Cosine is an even function. Sine of negative t is negative sine of t, because sine is an odd function. So you can simplify it as well, but I won't necessarily ask you to do that. If you want to make it to go around a circle in 1 unit of time, instead of 2 pi units of time, make it be a 2 pi t in front as the inputs for cosine and sine. Could you also switch the cosine and sine around? Sure. But if you do, you won't start at the rightmost point. You'll start somewhere else. In fact, if you make that a sine and that a cosine, you'll start at the top point. But in general, if A and B are different, you get ellipses, ovals. I might say parameterize an ellipse with this center and going through points here and here and points here and here. You have to figure out what A and B are if you did that, in addition to H and K. Should be able to parameterize lines. Use linear functions. It's helpful if you're going to parameterize a straight line to maybe figure out what X versus T and Y versus T look like first. I think we did an example like that. Draw graphs of X versus T and Y versus T first. Maybe X versus T looks like that and Y versus T looks like this. Figuring out the starting and ending points, their X and Y coordinates individually. Then figure out formulas for these two things based on the slopes and intercepts, and then combine them to get an XY parametric curve, which if they look like this, I guess it's going to look like that in the end. X goes from a positive value to a negative value. Y is going from slightly negative to positive. Something about like this is what the parametric curve would look like if these were your two component functions. Should be able to eliminate the parameter. Certainly with linear functions, it's fairly simple. In fact, when we, in the three-dimensional case, when we do the symmetric equations, solving for t, that's the way you eliminate the parameter with three-dimensional examples. Some examples are a bit trickier. The book does 1 or 2 of those, eliminating the parameters. Some involve cosine and sine, and so, like this example here, how do you eliminate the parameter there? Rewrite to isolate cosine and sine, and then square both of those and add them up using the Pythagorean identity there, and rewrite it in terms of X and Y. That's how you eliminate the parameter in that context. And that's a pretty important thing to be able to do. So I'm not ruling that out. And by the way, this equation is the equation of an ellipse. This does parameterize an ellipse. Sometimes you had situations where the motion was back and forth. You should be able to use your graphing technology calculator to see that if it happens. Next section was about calculus and parametric equations. That's pretty important there. I find the slope along a parametric curve, dy dx. We're not talking about the speed. We're not talking about dx dt or dy dt individually. We're combining them to find the slope in the xy plane at any value of t, as long as you don't divide by 0. You also could use this to figure out where is the parametric curve, where does it have a horizontal tangent? It would have a horizontal tangent when g prime is 0. And actually, oftentimes a vertical tangent where f prime is 0. Yes, slope is undefined for vertical lines. But as long as they're not both 0 at the same value of t, where the bottom is 0, you are going to have a vertical tangent. You should be able to find, yes, slopes of tangent lines and normal lines. There's the slope of the tangent. The normal line has a slope that's the negative reciprocal. Normal is another name for perpendicular. Okay. Orthogonal is another name for perpendicular. So is normal. Oh, crazy. Normal's used more often by scientists. Orthogonal is used more often by mathematicians, though both scientists and mathematicians typically know that they both mean the same thing, normal and orthogonal. There was also the formula for the second derivative, giving you the concavity, so to speak, of a parametric curve. In the end, you find dy dx first as g prime of t divided by f prime of t, then differentiate that function with respect to t, then divide the result by f prime of t. So it's like a 3-step process. Examples are in there. You should be able to use that. Arc length is in here. We've used this a fair amount, including today, just 20 minutes ago. Could also call it distance traveled. Here, you're thinking of T1 and T2 as fixed numbers, like an A and a B. But you should be able to be flexible like I was today and make the upper limit of T a variable. And maybe use a different letter here like tau or U or W, doesn't matter. Oftentimes these integrals are hard to do. Sometimes they're easy. The example we did was not too bad. This integral wasn't too bad. You should be able to do one at that level of difficulty. Sometimes these kind of integrals involve trig substitutions from Calc 2. I don't know if you remember trig substitutions from Calc 2. Actually, my Calc 2 classes, we've just been doing that recently. They're hard problems typically. Like even if f of t is t and g of t is even just t squared or something, so that g prime is 2t and you got to square that to get 4t squared, doing that integral is a big pain. I would not give it to you on a test. It's doable, but it's a big pain. It involves a lot of trig identities to help you solve it. So the focus here is more on, do you know what equations to use in what situations? And well, let's make it simple enough that the integrals are not too hard to do. But you should be able to do fairly simple ones like the one we just did today. Substitution. Sometimes this ends up being a constant speed, and so you're integrating a constant, and that's definitely easier. Like if f of t and g of t are linear functions for one thing, or if they're involving cosine and sine, like for a circle at a constant speed, you end up using cos squared theta plus sine squared theta equals 1, and you end up integrating a constant. I did talk about surface area, but if I recall correctly, there was no problems on surface area, or was there one? Was there one? Okay, I mean, let's say you should know this formula in certain simple examples. Should be able to use it. I think there was one problem. I'll double check that. We also talked about deriving the formula in class, but I wouldn't expect you to do the derivation in the test. Then we skipped ahead to chapter 10, which was mostly about vectors. in their most pure form. Cartesian coordinates. Feeling comfortable with 3D stuff? Am I going to have you draw 3D lines? I'd try to make it simple if I did. I guess I'm not ruling it out. But the problem with having students do that on tests is you get lots of bad drawings that you kind of feel guilty about taking too many points off of. So it's kind of like maybe best not to put them on tests. But you should certainly know the distance formula to find the distance between 2 points. It is a generalization of the Pythagorean theorem. In fact, the derivation of this formula involves applying the Pythagorean formula twice. I won't take the time to do that. Probably would not require you to do it, but you should be able to use the formula. We got our standard equation of a sphere involving that distance formula squared to make the square root goes away. There was tricky things to do that where sometimes you have to do completing the square. If you got a quadratic equation like this and you're trying to figure out what sphere is it. And I think I would do spheres instead of ellipsoids or hyperboloids or paraboloids, like I briefly mentioned one day. Just spheres. Essentially, completing the square helps you figure out the center and the radius because you put it into this form. It's a worthwhile algebraic technique that I could ask you to do that. There were other things like in here, like equations of cylinders. Well, what is the cylinder? Actually, they're talking about a more general kind of cylinder there. X squared plus y squared equals 1. When you look at that equation, you think circle, don't you? Unit circle in the xy plane. Well, guess what? If you're thinking of that as describing a graph in 3 dimensions, it's really a cylinder like this. Because z can be anything. The z doesn't show up in the equation. So it doesn't affect its truth or falsity. It's only the x and y coordinates that do. So you take the unit circle in the xy plane and translate it up and down forever, giving you an infinite cylinder. It's an important enough concept that I think you should be able to do that. Planes that are perpendicular to one of the coordinate planes, like x equals 2 is, well, parallel to the yz plane. So all the points where x equals 2. They're important enough that you should be able to do that. Then we moved on to more general, we didn't get into a ton of detail in section 10.1. Vectors, what are vectors? How do you represent them? What's the algebra like? How do you find their magnitudes? How do you normalize them? Here, the word normal means something different than perpendicular. Here it means find a unit vector in the same direction. Divide the vector by its length. There are all these properties. Do you need to know their names? No, that's not really the point of this course. I'd be happy if you remember the names, but I'm not going to test you on them. I think it is helpful to know the names. There's the I hat, J hat, and K hat notation. The next section was about dot products. Okay, dot products. Should be able to compute them with the formula involving the components. Should be able to relate it to the geometric formula involving the angle between the vectors. And therefore, you should be able to find the angle between the vectors, a very common kind of problem that I put on tests. Find the angle between these two vectors. The formula being this one, solve for the angle. You need the inverse cosine. Concept of orthogonality comes up in this section. And the fact that two vectors are orthogonal if and only if their dot product is 0. That's because of this. The dot product is 0 and the vectors u and v themselves are not 0. The magnitudes are not 0. So the cosine of theta must be 0. And that happens when theta is pi over 2, for example, 90 degrees. Or 3 pi over 2, 270 degrees, though we typically think of the angle between two vectors as being between 0 and 180 degrees. Projections are also in this section. Projection of one vector along a line to the other as a formula. Pretty important concept. Those who took DiffyQ with linear know we use projections a lot, especially near the end of that course. Be able to know and use this formula and be able to interpret it geometrically with a nice picture. I sometimes do ask for nice two-dimensional drawings. With two-dimensional drawings, you should be able to take the time to draw them nicely. Remember that the projection of one vector along the line to the other is like the shadow of that one vector on the other line, with light rays coming down perpendicular to the other line. There's the orthogonal decomposition. The key is this other vector is just u minus the projection, and these two vectors are orthogonal to each other. Pretty important concept, actually. Will be pretty important for us next week after the test in thinking about acceleration vectors for motion. This fact here. Yeah, there's physics examples, but I'm not going to test you on physics. Cross product. There's the formula. You could write it this way. You also could use the shortcut involving these diagrams. Or if you want to do the pure determinant way like I did at first, you could do it that way. Properties including anti-commutativity, pretty important. And you figure out the direction of a cross product with the right-hand rule. The opposite cross product points in the opposite direction. The fact that the cross product of any vector with itself is the zero vector. And in fact, any vector crossed with another vector parallel to it is the zero vector. This formula is important. You can relate cross products to angles as well. But it is a little different than the other one for dot products, not only with a sign there instead of a cosine, but also in the fact that this gives the magnitude of the cross product, not the cross product itself. Dot products are numbers, cross products are vectors. There's the fact that cross products can give you areas of parallelograms, and if you divide them by 2, also areas of triangles. And in 3D, they can give you volumes of parallelepipeds if you combine them with a dot product in this way. Not ruling out asking those kinds of questions. Common question I ask, here's 3 points. Find the equation of the plane that contains them. Next couple sections were about parametrized lines and planes. I think that's the most important kind of question. You got 3 points. Find an equation of the plane containing those 3 points. Start by finding 2 vectors parallel to the plane by creating displacement vectors between points by doing subtractions, appropriate subtractions. Don't make a mistake like I did sometimes. Then find the cross product to get a normal vector. And in either of these forms, standard form or general form, the vector with components A, B, and C is a normal vector. Effectively, this is using a dot product to see that the dot product of the normal vector with any arbitrary vector parallel to the plane is 0. And then if you simplify, you can put it into the general form. But in either case, the coefficients of x, y, and z are the components of a normal vector. Normal vectors are not unique. You can multiply them by non-zero scalars and get another normal vector. These equations are not unique. You can multiply them by any non-zero scalar and get another equivalent equation. And then finally into chapter 11. Calculus of vector valued functions, derivatives, and integrals. Derivative rules like we used for this example today. There's also just interpreting the derivative of a position function, giving you the velocity, and the second derivative giving you the acceleration. Should be able to plot them. Speed is the magnitude of the velocity. Integral of the speed is the distance traveled, also called arc length. And yes, a simpler example of an arc length parameterization like I showed you. Now, sometimes you had some other kinds of problems that I haven't mentioned. Like, here are 2 lines. Are they parallel or skew? Or If they're skewed, do they intersect or not? Parallel lines are easier to figure out because you look at the direction vector for the lines. If those are parallel, then the lines themselves are parallel. Are they the same line? You could use the symmetric equations to figure that out. If the lines are not parallel, they're either skew or intersecting. You want to effectively see if there are values of S and T that make these equal to each other. And if they're three-dimensional vectors, it's going to be three equations and two unknowns, which in general won't have any solution. So mostly for arbitrary such lines, they're not going to be intersecting. But as a teacher, I can make an example where they intersect. And so you'd have three equations and two unknowns that are solvable. You can find one value of S and one value of T where these are equal in terms of all their components. Then that's going to be a point of intersection. S and T could be different, but the point itself would be the same.